pleasure to introduce the first speaker of Giulio Biroli at the Università. Show us some new result of activated dynamics in Glassy systems.
Okay, so well, good morning, everybody. So today I want to talk about activated Glassy dynamics. Actually, I will talk about some new results, but also I will talk also about ideas and perspectives. So the results are with all these people in different papers: Achard de Lustrac, Marco Baitigliesi, Alain Bilouard, Chiara Camarota, Riccardo Ravasio, and Valentina Ross. The four of them are here. And then since I will talk about ideas and perspective, I mean, these ideas and perspective are, of course, mine. I mean, I take responsibility, but I mean, they came with discussion, a very helpful discussion with Gérard Benarous, Jean-Philippe Bouchot, Silvio Franz, and Jorge Kurchan. Okay, so let me first start with some non-scientific parts, so saying happy 70s, Giorgio. So I would like to, well, as Remy told the first time he met you, I mean, I also have a first time. Actually, in the first time you weren't there, I was in, actually, it was in my 5th year of university. I had an exchange program with the École Polytechnique in France. And I mean, I wasn't sure about much, but I was sure that I didn't want to be a nuclear engineering, which was the thing that I studied for 5 years before, and I wanted to do theoretical physics. And at a certain point, I didn't know actually what to do in theoretical physics, and actually even if I could do theoretical physics. And there was an article, I read an article by Dan Stein about spin glasses. And actually, it was a very good article, maybe the best I read of him. And and he was discussing a lot, I mean, this great Italian physicist. He discussed a lot your theory, the fact that it applies not only in physics, but also in neural network optimization problem. And this really motivated me on, well, doing what I do. And then actually I had to choose exactly at that moment the internship. And I mean, stars aligned because I opened the subject of the possible internship. There was one by Mark on the Bernasconi model and Glassy system without disorder. And so, well, that was perfect. And was really the beginning of my path. And I wanted to say this also because I think you were very important in influencing many people in the direct way, but also in an indirect way. And it happened to me many times during my career, even at the very beginning. So thank you very much. Okay, so now let me talk a little bit. So start about talking about activated dynamics in Glassy systems. So I think, the majority of the audience don't need an introduction, but okay, Glassy system, very broadly speaking, are interacting degrees of freedom with a very rough energy landscape. You find many Glassy systems in physics. I mean, example are glass-forming liquids, colloids, disorder magnets, and you will hear a lot about this today. But actually, you can find also in other fields like computer science, biology, and social science, and you had many examples actually yesterday, and I think you will have many examples tomorrow. So, well, the characteristic of Glassy system is, as I say, the rough energy landscape, a rough, high-dimensional energy landscape. And what you want to know typically is how the system, I mean, how the dynamics of the system evolve in this very rough energy landscape. In particular, what are the paths that the system has to follow to go to lower and lower energy. And now, especially if you do, for example, a quench to low temperature, what you want to know is really how the system jump over barrier and find path to go to lower energy. Now, jumping over a barrier activated by thermal noise is something that is very much well understood in simple cases in which you have finite dimensional system, you have a finite number of barriers, you have a finite number of critical points, and so depending of your background, well, you can use technique based on the degenerate vacua in quantum field theory or nucleation theory in statistical physics, or if you're a mathematician, you would say Fredrik Wenzel in probability theory. This is just to say that the problem when you have to jump, I mean, you are in a finite dimensional energy landscape and you have to jump barriers, everything is well understood. Now, the problem is that in the case of Glassy system, I mean, the energy landscape is extremely high dimensional. So the number of minima in general scale with like exponential to the number of degrees of freedom. So you have also an exponential number of saddles, you have also an exponential number of paths. And so in this case, all the technique and the concept that have been developed, let's say with a finite number of critical points, don't work. And one needs to develop new concepts and new methods. So this, I think, this is one of the reasons which makes challenging and very interesting from the methodological point of view, understanding activated dynamics in Glassy system. And then, well, of course, it has also, is very relevant because it's a key phenomenon in many different contexts. So just to give you an example, if you want to understand the glass transition, how liquids form glass and why the dynamics slow down so much, you really have to solve this problem, to tackle this problem. So, of course, I'm not going to give you any solution today. I will just tell you some results that have been found during the years and some ideas and some perspectives. So I think it's something that, I mean, an interesting point of view that, of course, was pioneered by Giorgio is that, I mean, to understand complex phenomena in Glassy system, one good thing is to focus on mean field models first. Because if you analyze mean field models, sometimes you can really find things that it was just impossible to guess a priori. And they give you a very important lesson. So let's start, so with the same idea, let's start to see what we can get, what we can learn about activated dynamics in mean field models of glasses. So just to be concrete, there are many mean field models, and I will focus here just to give you, let's say, again, I guess this slide is for the 70% is known for everybody, but for the other ones, it will be, let's say, a crash course. So I will focus, let's say, on a archetypical models, which is a mean field model actually of glass-forming liquids in a very abstract sense, which is called the p-spin spherical model. So you have spins, which are actually not spins, but they are soft spins, so they have just this constraint. So the configuration live on a sphere of radius square root of n, and then you have interaction, which is at p-spin with p larger than 2, and these are quenched random couplings, which are independent Gaussian variables. Now, in this case, which happens also in other case of mean field Glassy system, the nice thing is that rough energy landscape is not just the word, it's something that you can really analyze in a very concrete way. And well, to give you, well, I think it's in this field, one very important paper was this one by Andrea, Irene, and Giorgio in '98, in which, while they really started to go deeply on the statistical property of rough energy landscape. So what they compute is the number of critical points of index k. So a critical point of index k means that it has k direction in which, well, you can go down in energy, and all the other ones you go up in energy. So if so when k is equal to 0, you are counting minima, you are focusing on minima. Where k equal 1, you have a saddle with just one descending direction, and then, well, there are all the other values of k. So what they compute is the number of critical points of index k at a given energy density E, and this scale exponentially. As I told you, there is an exponential number of critical points in n, which is the number of degrees of freedom. And then you have this function sigma k of E, which is called the complexity of the critical point of index k. And here you have the different lines which correspond to, well, this is k equal to 0, k equal to 1, k equal to 2. So what you see here is something that is very interesting and non-trivial, is that, well, if you are in the regime which is between the ground state and this energy which is called the threshold energy, so if you take a critical point at random, this is typically a minimum. So there is an exponential number of minima, but still there is also an exponential number actually of saddle of index 1, and there is also an exponential number of saddle of index 2, except that they are exponentially less than the number of minima. And so while this is a cartoon, actually, I stole this actually from a paper by, this comes from the paper by Andrea, Irene, and Giorgio, but this nice picture comes from a paper by Patrick Charbonneau. So here, what it tells you, this picture, is that, well, if you are at the bottom of the landscape, you have just one minimum, and then when you go up, you have many, 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 and then actually when you reach this energy, you have a kind, you kind of collapse, in the sense that you have an equal number at the exponential level of minima and of critical point of any finite index. And if you go actually to an energy which is higher than this, then the critical points have an extensive number of direction which goes down. So this really tells you that, while the landscape statistically is very different if you are above this energy or below this energy. And this actually has very profound influence on the dynamics. So if you want to study now the dynamics in this landscape, well, what you can do, you can start from a random initial condition, let's say infinite temperature, and then you quench the system, which, let's say, satisfy a Langevin equation, so it's a couple to a thermal bath, and you quench it to a certain temperature T. So if T is less than a certain temperature TD, which is the dynamical critical temperature, then the system always stays out of equilibrium, at least on time scale that do not diverge with N. So on this time scale, actually the problem of understanding the dynamics has been solved, well, starting from the paper by Harg and Letizia in 1993, and then there have been many other also that contributed to this topic. And so what is understood is that actually when you start from very high energy, the system just go down in energy. It's not jumping any barrier. It's just, well, you have a, let's say, a extensive number of direction that falls down, so the system just go down. It finds, the longer is the time, the less direction the system finds to go down, so the system slow down. This is why you have aging. And then at long times, actually you reach, if you do a quench at very low temperature, you reach this energy, which is the threshold energy. So in this regime of time scale, which is you take n going to infinity first, and then you take t going to infinity later, you just don't have any activated dynamics. And this is something that, say, is very well understood starting from, let's say, 93 until now. I mean, there are still some open problems, but roughly, I mean, we know what's the picture for the dynamics. Now, instead, if you consider time scale which diverge exponentially with n, actually the system is able to go inside this region. And you have to consider actually time scale which scale exponentially with n, because the barriers between these states are for their n, big N. So, well, you have to go, I mean, activated dynamics takes place on exponentially large time scale in n. And so, well, what I wanted to tell you in the following is what we know and what we don't know, and what we can speculate about this regime, which is the regime of activated dynamics on exponentially large time scale. So to start, I will start with the lesson that one can get from the simplest rough energy landscape. So in this case, the nice thing is that it's problem solved. So there has been a long series of papers. Actually, was, I think, a nice complementary way to attack this problem. There have been mathematicians and physicists. So there are rigorous proof. There are, let's say, physical argument, and there are also simulations that really explain what's going on if you look at the activated dynamics in the random energy model. So this is the simplest spin glass, or the simplest rough energy landscape. It's been introduced by Derrida, and actually, well, I know from Giorgio that also Cabibbo thought about it, but he didn't publish any paper on this. So this random energy model is very simple. You have n spins, n Ising spins, so it means you have 2 to the n configuration. Each energy is a Gaussian independent, identically distributed random variable with this distribution, which means that the variance of the energy is n divided by 2, which means that the typical energy scales like square root of n. And then, I mean, you have to think, if you want to understand activated dynamics, you have to declare what is the dynamic that you consider, and the dynamics will be just a usual Monte Carlo dynamics. So at each time step, you take a spin at random, and you try to flip it with a rule that verify detailed balance. And so what I want to understand is, or what I wanted to tell you is, well, what is the dynamics of this system on exponentially large time scale? Now, for this model, the random energy model, I mean, here you can get a cartoon. It's just a cartoon, which is similar to the curve that I showed you before on the complexity given for critical point of index k. So I say this is a cartoon because, well, a critical point of index k, since these are discrete Ising spins, is not well defined. But I could try to define it somehow, saying that I count how many configurations I have, such that if I flip k spin, the energy will go down. Okay, so this, it's a very rough definition. And then you can, of course, you can always define minima. So you have a curve with the minima, which is this one, which is the complexity of minima, or if you want, this is just the entropy, actually. And then you can also see it to the other curve. And so you see here already a difference with what I showed you before, is that all these curves actually collapse together at energy 0. Yeah.
If I understand correctly, k equal to 0 is one spin.
It's one spin, yeah, exactly.
K equal to 1 is 2.
Yes, exactly. Yep. And see, this is just to show you that, I mean, energy 0 is special. Another way to see this, and again, the situation for the rough energy landscape is different from the p-spin spherical model. It's much simpler. And one other way to see it is that if you take a configuration at energy E, and you look where are the neighbor in energy landscape. Now a configuration in energy E, how many neighbor it has? Well, it has n neighbor, because with the dynamics, you know that the dynamics, what it does is take a spin at random and then it flip it. So you have n possible way to go out from a configuration because you have n possible spin flip that you can do. So each configuration has n neighbors, and these n neighbors actually, well, if you take this low, well, you know where they are, because they are at a typical energy, which is square root of n, roughly. And then it means that if you look to the intensive energy, which is divided by n, the intensive energy of all the neighbors of a given configuration at a certain energy are at energy 0, okay? So this means, in a certain sense, if you want, that the threshold is at energy 0, or in another way to say it is that the rough energy landscape, it's very simple, it's really like a golf course. So if you have a configuration at a certain energy E, is typically minimum, and all its neighbors are very, very high, which are at energy 0. So this also tells you that if you do a quench at finite temperature, the system starts, if you start from an infinite temperature, you start at energy 0, and there is no regime that I discussed before, like the regime that was discussed by Letizia and Jorge. So for the RAM, the dynamics is always activated. If you want TD is equal to infinity. So while in the case of the random energy model, yeah, dynamics is always activated, and you would like to understand, well, what is the picture that comes out for the dynamics of the RAM. As I told you now in the following, I will give you, well, what is the picture that has been understood in a, well, very, let's say, long series of paper. So I won't explain exactly how it was obtained. I will just give you the rough idea. So as I told you, if you consider a given energy level at a certain energy E, all its neighbors are at an intensive energy which is 0. Actually, you can maybe, well, you can focus a little bit how they fluctuate. And so the lowest in energy, the lowest value in energy is case like minus square root of n log n with some fluctuation if you use extreme statistics, but well, roughly speaking, they are always at energy 0, all at energy 0. So what this means is that if the system is in this configuration, the time it takes to go out goes like exponential minus e divided by t, because necessarily has to jump up to this level. And this, again, this scale with n, so this is why you have a time scale that are diverging with n. And then if you look at the system on this time scale, so if you do a coarse grain in time, actually, well, it's true that here there is a bit of difference in energy. So actually, in the real dynamics, what can happen is that the system go here, then it has to look at the neighbors, then maybe it come back, and then it go up again, and then it start to explore. So there is some complicated dynamics. But if you coarse grain, so if you look at the system just on time scale that are diverging with n, you can, I mean, the motion is like, I mean, when you go out, you have like free motion. So you can really assume that on this time scale, it's like if when the system goes out, it just take another configuration at random with the distribution that I gave you before. So you go out from this configuration with this time scale, and then you pick another one. So you, at random, it's just because you move to another one, and since energy are uncorrelated, this one is just a random configuration. Of course, this is not true really in the microscopic dynamic, but on coarse grain time scale it's true. And so if you have this, actually, well, this is nothing else than the trap model that was introduced by Jean-Philippe Bouchot in '92. So what has been shown, actually, in the case of the random energy model is that effectively, on time scale, which are diverging with n in exponential way, the effective dynamics is exactly the one of the trap model. And this has a very nice and interesting consequence, and which I think are probably, some of them are true also in other models. So the first thing is, which I think is very interesting, is that if you wait a certain time t, the system has reached a certain energy E of t. And now if you look to the probability, so the probability distribution of the configuration that are, I mean, the distribution of the configuration that have been visited by the system, this, I mean, you see that the system is exactly as if it was equilibrated on all configuration until energy E. So it means that here the probability distribution is just like Boltzmann, But then, of course, I mean, if you are at a certain temperature T and the equilibrium energy is here, the system is not at equilibrium. But it's as if it was at equilibrium, but I mean in a restricted way. So just up to, down to this energy, E of T. And then if you zoom actually on what happens, how is the distribution here, the distribution of the configuration around the energy E of T, well, what you see is that exactly like a 1 RSB, so one replica symmetry breaking distribution, which has very specific properties, but with a parameter m, which actually depends on time. It's actually related to the slope here that you have here of this curve. And the other important thing is that how the energy, actually after a time t, what is the value of the energy? Well, this is something that is given, it's clear in the trap model. And so what you have in the trap model is that the at time t, the average energy is dominated by the lowest trap because the system stays for, let's say, a very important fraction of time t in the lowest trap. And so, while if you are at the time t, well, you know that the time you stay in the lowest trap, it's of order of exponential minus E of t divided by the temperature. And so this is the energy of the lowest trap you visit on a time scale t. And if the lowest trap is dominating the average energy, this gives you this relation, which is that the energy goes down in a logarithmic way with time. So now you have how the energy goes down in time. So this will tell you what is the value here where you are. From this, you can get the parameter m, which gives you the 1 RSB-like equilibrium measure. And then also you can get a correlation function from this, which is the correlation function that you find in the trap model, but which in this case is true actually for the random energy model, with the parameter m, which is this one. Okay, so you have a complete picture actually of what's going on in this case for the activated dynamics. And you have a nice relationship actually between aging and activated dynamics and equilibrium, but with, again, a parameter which depends on time. Just one final thing, so when you start, so m depends on time, and so it starts at value 0, and then if you have a temperature T such that here is the equilibrium value of the energy, so m will increase and will reach value 1 exactly where you reach equilibrium. Okay, so this is just to show you that you can see also in simulation this. You can, you can do, if you do in simulation the coarse grain that I told you, so you have to coarse grain a little bit on time, and then you define basin. So this is, let's say, it's a cartoon of the energy as a function of log of time. So let's say that you are in one basin, and then you can try to look what is the energy and the trapping time of, let's say, the next basin, so then basin number 1, the next, which is basin number 2, and next, which is the basin number 3. So if this is like in the trap model, what you should see, since when in the trap model you have renewal property, is that the energy of the following basin should be uncorrelated, and so, the energy of, say, basin number 1, basin number 2, or basin number 3 should be independent of time, because it's just as if you are picking at random a new configuration. Similar thing for the trapping time. So here you have this is, forget about the red curve, the black curve. Here is the energy of the basin number, the following basin, and you see it does not depend on time, so it means that the system is going down in energy, is going deeper and deeper, but the next basin is, well, it doesn't depend on time, because you just go very, very up in energy. Yeah. So the following basin is just very up in energy. And similar thing for the trapping time, tau 1, tau 2, and tau 3. So for the black curve, you always get that they're independent from where the system is. And this you could think that is very peculiar, because if I'm very deep in energy, why the basin where I jump should be independent from where I am? And this is really due to the random, the simple feature of the energy landscape of the random energy model. Okay, so actually this kind of effective trap dynamics that you find in a model in which the microscopic dynamics is not like in trap has been found also in other models, and there is a nice paper by Chiara and Enzo, maybe 2017, not 2019. Okay, so now, while this is what happens for the random energy model, and in this case we have a clear picture, and again, as I told you, there are simulation that works, there are physical argument that works, and then there have been even proof. Now, if the problem is that this energy landscape is very simple, so one would like to go beyond and to study what happens in, let's say, energy landscape which are more characteristic of mean field system that we use, for example, to explain the glass transition or other system. So I go back then to the p-spin spherical model, which is again an archetypical model for many different transitions, even it's very simple. And again, well, what we know is, well, this curve with this cartoon representation that I discussed already. But now, if we want to understand activated dynamics, I mean, it's not enough to know, well, that at the given energy, I have a certain number of minima and a certain number of critical points. What you want to know is, for example, if I'm in one minimum, how this minimum is connected with critical points. In particular, you would like to know, for example, what is the lowest barrier that allows the system to go out. So really, ideally, what you would like to know is not just the number of critical points or the given index, but you really want to know how all these points are connected, which is, how the configuration space is partitioned, looking at the way in which critical points are connected. So for example, what are the critical point of index 1, which are connected to one minimum? What are the critical point of index 2, which are connected to a given critical point of index 1, and so on and so forth, which in math is called the Morse complex. So, well, of course, we are not going to, what we are going to present you are some results in this direction, but we don't have the complete solution. So these are results actually that appeared in a paper that we passed last Monday with Valentina Ross, who is here, and Chiara Camarota, who is also here. So what we do is, well, exactly what I told you. So we take an energy minimum, let's say at the given energy, which is here. We'll call this minimum sigma, the configuration is sigma 0, has a certain energy, E0. And then what I want to know, I want to explore around this minimum, what are the critical points? And also, what I would like to know is, especially, what are the critical points which are associated to barriers? So what are the saddles of index 1, which has a direction that brings me into this minimum? So this means computing the complexity of critical points at a given overlap, which means at a given distance from sigma 0. And also I want also to know what is to fix their energy, and I will call it epsilon. Okay, so this actually is a computation which is called constraint complexity, which was done 20 years ago by Andrea, Irene, and Giorgio. And so what they compute is exactly the function, well, this complexity of so critical points at a given overlap, at a given energy with respect to a minimum at a certain energy epsilon 0. So what they did is to compute the annealed, actually, the annealed complexity, and they use a method which is introducing bosonic and fermionic variables. So what we did 20 years later, so we tried to do this a bit more. So we used a different method, which is what we call is the Katz-Rice method that has been become very fashionable in these years, especially in math. So we did a replicated version that we introduced in this work in such a way to compute actually the quench complexity. So really to compute, it's really the quantity that you would like to study. And this method is, has some good property compared to the usual method that has been used before. One is that it's avoid of subtleties. So as Florence said, when he was here in postdoc, there have been a big debate that then was solved about, whether when you compute with bosonic and fermionic variable, which kind of solution you have to get, whether you should consider supersymmetry breaking or not supersymmetry breaking solution. And all this has been understood, but it's subtle. In this case, you don't have to ask all these questions. The things are quite straightforward. And also the nice thing is, for people that like it, is that at least in the annealed version, it can be made rigorous. So the nice thing from the point of view of physics is that with this method, actually, we can really have a very detailed analysis of the action of the critical points. And as I told you, I want to know what are the barriers which are related to a given minimum. So to know what is the barrier, I have to know that the critical points around, I want to know whether they have an index 1 saddle, and especially I want to know whether the direction of the index 1 saddle is pointing toward the minimum. And this is what I'm going to tell you now. And then there is also a nice result. Nice, it depends for who, but so what we found is that after you do this big and complicated computation, at the end you find that quench actually is equal to annealed, which means that what they did is not an approximation, it's really the correct result. And I still don't understand why quench is equal to annealed in this case, and I thought at least in their paper they also say that they did not expect to have quench equal to annealed, but that's what we find. Okay, so let me tell you the results. So, well, I have many figures here, so let me walk you through. So the first thing that you find, which is kind of normal, is that if you take an energy minimum, sigma 0, if you're very, very close to this minimum, you don't find any critical points. So the landscape is convex, is just harmonic, and then maybe you would start to have something which is non-harmonic, but you have to go to a finite distance to start to find critical points. And so what I plot here is what I call isocomplexity curve, which means that I'm plotting the energy of the configuration which have a complexity equal to x. So let's focus, for example, on this curve. This curve is the isocomplexity which corresponds to x equal to 0, which means that I'm plotting actually the energy of the lowest, I consider all the critical points at a given distance q, and a given overlap q, and I look at the one which have the lowest energy, which also have the lowest complexity, which is 0. Okay, so these are the lowest one that you can find. And then, well, the nice thing is that, as I told you, is that we can understand what are the property of the Hessian. And so what you see is that along this line, first, when the critical points appear, they appear at high energy, and they are barriers, meaning that they have an Hessian, which is, well, this is the distribution of the eigenvalues. The distribution of the eigenvalue is a semicircle, is a positive semicircle, but then it has one eigenvalue which is negative, which pops out. And if you look to the eigenvector, which is associated to this eigenvalue, actually has a component which is has a macroscopic overlap with the direction of sigma 0. So it means really that when they appear, so you have this, well, very high saddle, which has a descending direction, which is in the direction of the minimum sigma 0. And then, well, if you still have, this, so you still have an eigenvalues which is negative with the direction which points in toward sigma 0 until a certain distance or certain overlap q, and then the eigenvalue it becomes positive, so this is no more a saddle, it's no more a barrier, it becomes a minimum, and then so all this part of the curve actually correspond to minima, and all this part here which correspond to purple, it correspond to barrier. And so here you see that you have a similar thing also for critical, when you consider isocomplexity curve with x which is positive. So, well, at the end, so really what this means is that when I consider a minimum, I look around, close to me there is nothing, and then up very, very, very high, there are some barrier that appears, and then if I go to a distance which is a little bit farther, I can find barrier which are at a lower energy. I go a little bit farther, I can find barrier at a lower energy, and then this point here corresponds to the lowest barrier that one can find. And so the other important interesting thing is that we can compute, so if I zoom on this region, and here I have a color plot of the complexity in the, let's say, epsilon and q plane. So here is, again, what you see. So when it's blue, it means that the complexity is very small. When it's red, it means that the complexity is very high. So it means that when I go, well, far from a minimum, when critical points start, they have complexity 0, so there are very few, that's normal. Then if I go away, then the complexity start to grow, and then if I go very, very far, then the complexity is very high. So this is the behavior of the complexity of the barriers. And then what I can also tell you, which was also actually studied by Andrea, Irene, and Giorgio, is how these things, actually this curve here, I think even if they didn't plot it, they had it. And so what we have more is really the behavior of the Hessian. So you can look at two characteristic energy. You can look at here, what I plot is the energy of the barrier when it appears. So the first barrier that appears, which is called, well, is this value here. And this is the value of the energy, which is the lowest barrier that you can find, which is the energy here. And this as a function of epsilon 0, which is the energy of the minimum. So you see that you have a big spread when the energy of the minimum is the ground state. And then when you go up in energy, these two values approach one another, and they become equal, and they become equal to the threshold when the energy epsilon 0 becomes equal to the threshold. Because at the threshold, actually, well, as I told you, you have a collapse of all the different critical points of any index, and so the barriers actually disappear. So, well, the message from this, well, first let me tell you something, is that this has been obtained with the Katz-Rice method, but there is a way to obtain this, result related to this with a replica potential approach, but one has to also to study large deviation, and this is something that Silvio and Jacopo have done. So the summary here is that what we have, thanks to this analysis, is that we know what is the lowest barrier to escape from a given minimum, and we know that this is lower than the threshold. So this is clearly different than in the random energy model. So if I look to, let's say, how to escape from a given minimum, I don't have to go up to the threshold. I can go to a lower value. And then, well, the other thing which is important is that we find an exponential number of barriers. And this is something, again, that I think it's very interesting, because if I look to the dynamics at finite temperature, exactly like for thermodynamics, you have to understand the balance between entropy and energy. Here you will have to understand the balance between the entropy of barriers and their energy. So, I mean, it's not clear that you always want to escape from the lowest barrier. At finite temperature, maybe it's useful to go to higher in energy. So this cost, because the rate to escape is exponential minus E divided by the temperature. But still, you have so many barriers that it can be useful. Okay, so, well, now, this is just to tell you that we have some information now on the energy landscape of the p-spin model to try to understand activated dynamics. And what comes from this is that it's a bit different from the one of the random energy model. So one can ask, I mean, is the dynamics different? And one way to try to answer this question is to do a numerical simulation. So since I show you that in numerical simulation in the RAM, if you coarse grain, we can really see emerging the trap model, while we can see what happens in an Ising p-spin. And while here again, for comparison, is what you get, again, forget about the red curve. For the black curve is the trapping time of the next basin or next to the next, and etc. And this is what you get. Here, I mean, what we do is that, we have to define a certain threshold. We have to define basin. So to define basin, we have to say that, we have to put a threshold. Well, we know where the threshold is when n is equal to infinity. When we do a simulation, it's finite, so there is always some fluctuation. It's not clear what the threshold is. So the curve that you have here correspond to different guess on the threshold value. And the interesting thing here is that these three curves correspond to tau 1, tau 2, and tau 3. So you can see two different things. So the first important thing is that these are as a function of the time after the quench. So this means that after a long time, the system has to go very down in energy. But then the time scale of, then it goes out, it goes to a next basin. Now the time scale to go out from this basin actually depends on the time. So it depends on the energy actually at which the system is arrived. So the lower is the energy, so the longer is the time, the lower is the energy at which the system has reached, and the longer is the time to escape from the next basin. So this means that the situation is very different from the random energy model, in which you just jump out to the threshold. Here it looks like that you jump to a basin which is below the threshold, and so there is still, and I mean, the longer is the time, the longer is the trapping time of this basin. So this clearly is different, while you can see that, if you look to the following basin, there you have another curve which is a little bit smaller, so the time scale to escape from the second basin is a bit smaller, but I mean, things are not changing much. So it looks like that maybe the scenario in this case is different from the RAM. So, what I wanted to do in the remaining time is, tell you what, then okay, the results part is finished, and one can try to think what is then the scenario that might be correct, and that we should maybe try to prove that it's correct with doing different works. So I think it's very reasonable to have, the property that I told you about the random energy model is that you have a kind of equilibration, partial equilibration until a certain energy E, and then if you zoom around the energy E that the system has reached, you have a 1 RSB-like measure. So this, I think, is, first is natural from a general point of view. And the reason is that, when you know that to reach a given energy, it needs a very long time scale, which is actually is exponentially longer of the time scale to reach the energy which are above. So from this point of view, once you have reached an energy which is E, it looks reasonable that you have equilibrated completely in all the energy which are above. And then, the fact that you have a 1 RSB-like measure, this is, it's not trivial at all, but there have been a series of work, very nice series of work at the beginning of 2000 by Andrea Crisanti and Felix Ritter that studied the random orthogonal model on timescale which are diverging exponentially with n. And they wanted to know, what is the what are the main feature of the dynamics. And so they found, for example, that here the system age with an effective temperature that is really given by the slope of the complexity, which really hints to the fact that around here the distribution is 1RSB-like with the parameter m, which depends on time and which is related to the slope of the complexity. Then, well, there is something which is different. Okay, so this would be similar to what you find in the random energy model, and something that is clearly different, probably, you don't have to go up. So when you go out from one minimum, you jump to another basin, and then maybe you don't have really to, you can, let's say, move below the threshold and then reach another minimum, which is completely uncorrelated and the same energy with this one. And so this means that, I mean, there is something that we really have to understood, which is what is the height of the highest barrier, which is crossed, that this depends on the initial energy, and also how to manage the interplay between the complexity of barrier and their height to understand activated dynamics at finite temperature. So for example, in this case, we don't know exactly how to predict how the energy would depend on time, because we don't know what are the barriers that are that are chosen by the system to investigate, to explore the energy landscape. Okay, so now we'll conclude. I can just tell you what, there are many maybe ways to go forward. This is what we are doing. So one way to try to go forward is to go forward in the analysis of how critical points are connected one with the other. So in particular, we want to compute the complexity of atypical barrier, which means what we did, the computation that we did is to, Okay, here we compute the typical critical point at the distance q. So for example, at this distance, q, we have the typical critical points are minima. But if you go up in energy, again, the typical critical points are minima, but maybe there are an exponential number of barriers. Well, the only thing is that they are exponentially less of the number of minima. So if we can show, for example, that here we have barriers, and these barriers allow to jump out from sigma 0 and go down, then, well, we know for sure that the energy landscape is very different from the one of the RAM, and the system does not have to jump to the threshold to equilibrate. Okay, so while this is one way to go on, so do other computation along the line that we did on the critical points, then I think it would be very nice to do other numerical investigation on the transition path that are used by the system, so this on finite system, and also on activated aging dynamics. Well, this can be done in let's say simplified models like the p-spin or the random orthogonal model, but it can also be done actually in real systems. So now you can do a big jump and you can look, for example, to a supercooled liquid, a model of supercooled liquid, and then study its dynamics from the point of view of the energy landscape. This has been done. And then, well, try to compare the result that you find in that case with the result that we find in mean-field system. And then the final thing, which is also a thing that we are starting, is try to develop a theory of the dynamical path followed by the system using field theoretic methods, which means try to do instantons, but on two-point correlation function, not just on trajectory like you do for in the case in which you have a, let's say, finite number of barriers. And with this, I thank you for your attention.
Of course, for each minimum, there must be at least one saddle. So a naive thing that one could imagine is to take the Cavagna, Giardina, Parisi plot that you have shown many times, to draw horizontal lines and look at the difference between the energy of the minimum and the energy of the first saddle. So how this compares with the minimal energy of the saddle that you find?
So it's not the same. We did it. Yeah, it's not the same. So it means that really there is some non-trivial organization in phase space.
Okay.
Yeah.
So you said that even for the random energy models, they are you need to coarse grain to get the trap dynamics.
Yeah.
So don't you expect the same thing for the p-spin? In other words, could you do a numeric for the random energy model and see how the curves look like? and see whether you need time to reach
Yes.
potential?
So yes, that's a very good question. So this is why I would say indeed that the jury is still out. It means that, well, I mean, it's true that, I mean, I go out from one basin, but then maybe actually what happens maybe is that I go to another basin, which is up, another basin, which is up, and then at the end, I mean, I really, if I want to go far away, I have to go to the threshold. So the threshold is sucking up the system. And so if I coarse grain on this time scale, maybe I get the trap again. So I don't know. That's really, I think it's a very interesting question. I mean, here you see that, I mean, tau 2 and tau 3, I mean, if this was true, it means that once you go, I mean, you look at the following basin, at a certain point you should get a straight line. Well, this is far from a straight line, but maybe you have to consider a lot of basins. So I agree, it's not clear that at the very end, we don't have to go up to the threshold. This is also why computing the complexity of a typical barrier could maybe give the final answer, but yes.
I also have a question. So the analysis you have done is on a mean field model.
Yep.
So what I'm asking is that is giving your result are giving some hints on what could happen in finite dimensional system like supercool liquids, where you rather tunnel the barrier than jumping over the saddle.
Okay, so the fair answer is no. I mean, we don't even understand the p-spin, so the supercool liquids are unfortunately far away, but I hope that once we understand the p-spin, we can understand the supercool liquids. So, I mean, if we knew, for example, how the system select the barrier in the p-spin, then maybe we can try to start to do well, first you could say, okay, if the system in a supercool liquids, you have the point to set length scale, maybe over the range which correspond to the point to set, the system is behaving in a mean field like way, and so there you can try to make a connection. So this is one possible way to try. But again, I mean, so another way, if we understand really how to do and to analyze the p-spin, then the next following step is to do the CAS model that Silvio studied a lot. So that's the idea, but I don't have any answer on this.
It is clear that one of the very relevant questions is where do you go after you cross the barrier?
Yeah.
And it's clear that this is a minimum time to do something.
Yeah.
But on the other hand, there was another paper with Irene and Andrea. We were fixing the distance with the final, from the starting point to the final point. We were trying to estimate the barrier from going to that point to another point.
Yes.
Have you tried to look also to that approach?
So, I mean, we read the paper, but no, we didn't try. I mean, the fact is that, but we should think more. The fact is that with the free replica potential, you cannot get actually what we get, because the fact is that when you do the free replica potential, the replica number 3 falls in a minimum, which is atypical from this point of view of this computation. So what one should do probably is doing the computation as Silvio is doing, so doing a large deviation on the free replica potential and then compute the barrier as you did. But it's, yeah.
Okay, thank you.
Okay, so thanks. Time is over for questions, so thanks again. Now the next speaker is Victor.